Another company called Tony Devaney Associates. I don't know how he could survive by doing theory, but he did. He's a recognized expert in the areas of inverse problems, diffraction tomography, subsurface imaging. He has an NSF center at Northeastern on this subject. And a few years ago, he was doing time reversal imaging method. This is the reason that we invited him this evening. And he has published many papers with the second patent and the Fellow of Optical Society of America. And the editorial, I don't need to read all these, but he has also obtained the best paper award. He has done a keynote speaker. He has been a keynote speaker and so on. Okay. And so we are glad to have Tony here to give a talk on the areas of combined physics-based signal processing type of stuff. Please. Thank you.
Is this the current department chair? Who's introducing? Who's this?
Well, first of all, I want to thank Professor Ishimaru for inviting me at such a great event. I've known Professor Ishimaru for many, many years, having first met him in the 1980s at Schlumberger, where he was one of our distinguished visitors quite a few times. I'll never forget the time in around 1986 when we were both attending a meeting in Washington, D.C. On rough surface scattering. And he was coming to Schlumberger in Connecticut, and of course I was going back, so I offered to give him a ride from the airport. And foolishly he accepted. And of course I got totally lost. I can't find my way from point A to point B. And he was so polite the whole time. It took us 3 hours to get from the airport to Schlumberger, and not one bad word the whole time. So the last time I was here was just about 20 years ago, where I gave some lectures and spent time with Professor Ishimaru. And of course I see him quite a few times in professional meetings and so on. Today, I decided to give a talk that I titled Physics-Based Imaging and Wavefield Inversion, thinking that there probably would be students in the audience, and I didn't want to get too technical, and wanted to give a general overview of some of the type of things, research that I do. I last gave this talk last year at the Naval Postgraduate School in Monterey, and it was well accepted, so I made some changes, but I think it's reasonably understandable. I'm going to talk about a unified approach to do many, many problems in imaging and wavefield inversion that occur in a number of applications. I'll start by talking about imaging planar and 3D objects. Then go on to wavefield tomography and inverse scattering. Then inverse surface scattering, and I put that in red because I'm going to spend some time on that. And then I'll go beyond Fourier. All of these topics we'll see, at least within the context of the beginning of the talk, can be easily understood just using Fourier analysis. Why Fourier analysis? Well, first of all, I just show you a function f of r of some 3-vector r position vector, and it has a Fourier decomposition here that I've shown. Here, and this is the Fourier transform. It's a function of a vector k, and of course it's related to the function of the inverse Fourier transform. Many of the problems we're going to be studying today, virtually all of them, can be cast in the form of, you know something about this Fourier transform over some region of space, and you want to generate an estimate of f, and the easiest thing you do is you just integrate that over the region of space where you know the function. But this looks easy, but in fact, in practice, it's not so easy because there are tricks involved. Many times, these are complicated regions. And also, you want to take this basic formulation and convert it to an algorithm that can be done quickly and efficiently, and that involves some work. Now, why does this simple Fourier analysis apply in wave propagation and scattering? Well, in the beginning of the talk, it's because we're going to restrict our case to where we have scatterers, objects, sources, or whatever embedded in free space in a homogeneous region. And in free space, the waves satisfy the homogeneous Helmholtz equation at some given frequency. K is the wave number, 2 pi by lambda. Because of this, you can show that these waves, wave fields that are generated, can be always expressed as a superposition of plane waves, where K has a magnitude equal to the wave vector, but of course is a vector, a 3 vector. And we're going to find that these are called plane wave expansions, and we can represent fields in homogeneous regions of free space, where these plane waves are homogeneous plane waves pointing in all directions. Or we can take a source and let it radiate out, and then throughout a half space we can do the same type of expansion. But we're going to find we're going to have to include evanescent waves, waves that propagate up and down the plane and decay exponentially away. But all of these type of problems, radiation, scattering, as long as they're embedded in free space, we'll admit these expansions, and you see the close connection here. The only difference here, I have a d cubed k here, and this is an integration that has only 2 degrees of freedom, which is, again, getting back to the case that we have a restricted region R. At the end of the talk, I'll tell you how to extend all of this to where it's not a homogeneous region and we have media involved. But of course, the mathematics gets a bit more complicated and so on. Now, there's 2 types of plane waves generally that we have to worry about. They all satisfy this equation, the homogeneous wave equation, the Helmholtz equation. However, some of them decay exponentially. They're called evanescent waves, and on the previous slide that I showed here, those are the waves that propagate into a half space, and they look like normal plane waves going up, but then they propagate up and down this plane and decay away. Those are called evanescent waves. So you have to worry about both homogeneous plane waves and evanescent plane waves. One way of looking at it is we take a plane wave, call it psi of r, and we write it with an amplitude and e to the ik. This is k dot r here, where I've used polar coordinates. So I write the r vector in terms of rho, which are position on a plane, and z. And then I write the wave vector in terms of its transverse wave number, which lies on this plane, and its wave number along the z-axis. Now, since this total wave number, k sub rho gamma, must have a magnitude equal to k squared, this and this are coupled through this equation. So this gamma guy, this z component of the wave, is given by this quantity, which is pure real, if k rho is smaller than little k, but it's pure imaginary. Otherwise, these are the propagating waves, because this is a pure phase factor. These are the evanescent waves. They decay exponentially with z. So we can look at this very easily. This plane wave propagates out at some angle theta. It has a gamma component and a rho component. Yet when the angle theta reaches 90 degrees, that gamma component becomes pure complex, pure imaginary, and these waves travel up and down, and they attenuate with propagation. So how can I use this to look at propagation in free space, which will get us to the problem of imaging objects, what we call coherent imaging on a computer? Well, let's say I have a plane, say, that I've denoted here by sigma naught, and I have a boundary value of a field that's a function of rho on position on that plane, and let it propagate away. Well, I can represent it in the superposition of plane waves, as I've shown here. Each of these is a plane wave coming out with an amplitude and its plane wave component, and the total field is given by a superposition of those. I've got to sum over all the k rho. And it turns out, if you look at this, again, Fourier, if I look on the plane z equal to 0, I can inverse Fourier transform both sides of this. And I found that this plane wave amplitude is simply the spatial Fourier transform of this field on the boundary. It's the spatial Fourier transform. So psi, this total wave that propagates away, it has a very simple representation. It's a 2-dimensional Fourier integral. It has an amplitude, which is the Fourier transform of the boundary value field, and it propagates away with that phase factor e to the I k sub rho plus gamma. Here again, I reproduce that, and here is a picture of that. The waves that are coming away from the plane are both homogeneous waves when this k rho is smaller than the wave number, and evanescent waves propagating up and down. And again, here's a picture of it going out like so. Now, if I look at this expression, you should see that if I Fourier transform both sides of this equation over any plane, not just the sigma 0 plane, any plane, I find that the Fourier transform of this is related to psi naught through this simple equation. This is an extremely important equation. It says the Fourier transform of the field on this plane is equal to the Fourier transform of the plane on this plane times a simple phase factor, e to the I gamma z, where z is the distance between the two planes. Now this gamma has two things. For the propagating waves that aren't evanescent, it's just a pure real number. For the evanescent waves, it's pure positive imaginary. So free space propagation corresponds to low pass filtering of this field, because you see in the evanescent region this will decay exponentially, and you'll lose all these high frequency, spatial frequency component of the wave as it propagates. So you lose detail, structure smaller than a wave. Now that's propagation, so I know how to take a field and go forward. What about going backwards? What if somebody gives you the field out here and tells you to go back and determine what the boundary value field that you started out with? We call that back propagation. Back propagation. So how can we do back propagation? Well, you see the answer is very easy. Here's that expression I had on the previous slide. The Fourier transform of the field on this plane is equal to the Fourier transform of the field on that plane times this phase factor. So I can solve for the Fourier transform back on this plane. Just multiply by e to the minus I gamma z. So you see, I can back propagate. I measure the field out here. I Fourier transform it, I multiply it by e to the minus I gamma z, I get the Fourier transform back here, and then I just do an inverse Fourier transform. The problem you see though is e to the minus I gamma z. In the evanescent region, gamma is positive pure imaginary, and this thing is exponentially growing. So back propagation requires amplification and is unstable and ill-posed. So we can't deal with those evanescent waves, we have to lose them. No matter what we do, we will lose those evanescent waves. Here is a picture of propagation and back propagation. Propagation, back propagation, and there the expressions for them are. Propagation is very easy to do, it's very well posed and well stable, and the back propagation is not, and you have to limit your integration to homogeneous waves or you'll have an unstable result. Now how can we use this? Well, one of the things I work on is developing digital microscopes and an optical microscopy. And one of the big applications of this is optical microscopy, and let me explain this a bit. Here it shows a simple model for a microscope is simply a lens, and you have a condenser which illuminates some object, and then you have an image. Now, how well does a normal microscope work? Well, it actually doesn't work very well at all. First of all, the illuminating light. You start out with a condenser source, and it's spatially incoherent. What we mean by that is that the radiations from different points in the source are uncorrelated. However, there's a thing called a Zernike theorem, and as soon as this light propagates even a small distance, as long as it's many wavelengths, this field will tend to be coherent. It'll build up coherence in the field. So what happens is, because of that, the light is spatially coherent over small regions, and you get a complicated, nonlinear relationship between your object and your image. It's partially coherent. Partially coherent light is very difficult to deal with. You get poor image quality. If this object is thick this way, your image quality is awful. That's why you have to thin slice to get good quality. If you have a phase object, what do I mean by a phase object? It's one that only affects the phase of the field and not its intensity. You can't image those because you'll just get, if it's phase here, you'll just see virtually nothing in the image. So you have to stain samples. you require high quality optics. I show a single lens, but a real microscope has many, many lenses all put together in a fancy way. So this is a very, very, very complicated, expensive operation. Doesn't work well. So what's the idea? Remove all image-forming objects and do it digitally. So here it shows on the top an analog imaging. Here's your thin, let's say we have a thin sample and we illuminate with a coherent wave, and this wave produces, this interaction produces a wave propagating out. Here's a lens. Nature forms the image. Nature does the back propagation. It's basically doing back propagation to get the image of the object. Here is now we're going to do it differently. We're going to let the light come out, but we're going to measure the amplitude and phase over here. We'll talk about how we do that in a moment. And then we use a computer to form the image via the process of back propagation. So the idea is, again, here is the object. We measure the field here, we back propagate, and we get our image. And there's our reconstruction because we've used the back propagation algorithm. Now there's one fly in the ointment, and that is we make our measurements with a digital camera, and it has finite extent. So you have a limited, what we call numerical aperture. You can't measure all the plane wave components. So you only can measure, you can't even measure all the homogeneous components. You can only measure those plane waves that enter an acceptance angle of theta, which leads to a bandpass on this of k sine theta, which is called the numerical aperture. But that's, you have to deal with that however you can. Here shows a diagram of a simple digital holographic microscope that I have in my laboratory. The one we have now is a little more fancy than this simple diagram, but I'll talk about that a little later. We have a laser, a spatial filter, a lens. Now, here's an interferometer, and the light gets split into two legs and is then combined to measure at a CCD, monochrome CCD. Here we put our sample that we want to image in this leg of the interferometer. Now, the problem with light is you can only measure intensity. You can't directly measure phase. That's generally called a phase problem. So what we do is we make measurements of holograms, Gabor holograms, and we make multiple holograms, and from those set of holograms we can get the amplitude and phase. This whole area has really grown in the last 4 or 5 years. It's called phase shifting holography, or phase shifting interferometry. What we do, originally we had a quarter wave plate. We either had this plate in or not, and we only made 2 holograms. And from the 2 holograms we were able to get the amplitude and phase and then back propagate to form the image. This just shows you the mathematics behind going from the measured intensities, or holograms, to the complex phase fields, and it's just a simple operation. Again, we have to deal with limited numerical aperture. You see, this CCD camera has a very small face. Here's our sample, which is necessarily set back some distance. So we have a limited numerical aperture, and for our system that I'm going to show today, which was an early version of our system, our NA was only 0.13. We're up to about 0.9 now, but that won't affect anything. Here is, at Northeastern University, we have a thing in electrical engineering called Capstone, where the undergraduates have to do a project each year. We call it the Capstone project. So this is my postdoc, one of my postdocs, and this was taken 3 or 4 years ago, actually. He's now at the medical school at Stanford. These are undergraduate students that I had at the time. This guy just finished his PhD at MIT. He is a big deal now at one company on the outside of Boston, and he's finished his PhD at Michigan. All 3 of these students had QPAs. I got very good students of 3.9 or above. This guy almost had a 4.0, but he took a graduate course from me while in undergraduate and got a B+. His father has never forgiven me. His father's a professor of mathematics at Northeastern. Here we start with a very simple example, a 5-micron slip. This is one of the first examples we did. This shows the 2 holograms of that slit, and this is just the scattered intensity that you get if you don't put an interference in. Here is the reconstruction you would get if you used standard computed holography, digital holography, and it's not very good. Here is ours, and you can, just by looking at it, see it's very good. I have a number of these examples. Here's a wonky ruling, 10 lines per millimeter. This is the scattered intensity, 2 holograms. By the way, we now use 5 holograms. These are the reconstructions we've got. This is phase shifting, phase shift in digital holography. That's ours. This is conventional microscope image, and you can compare these two. I have a better comparison below. This is a computed digital holography, and we do much better than digital holography, and the other is in some other scheme. This shows a comparison. This is what you would get with a conventional microscope, and this is what we get with ours. And you can see, we see detail that really is not there. But the real advantage of this is we can image phase objects, because we do it digitally. We can separately image the real and imaginary parts of the object. When you do it with an analog system, you only get intensity, and you can't image phase. Here is a salt water specimen. Here's a phase image. Here's a phase image colored in black and white, and the intensity images. But we could go on. I have a bunch of these, but I think I'm going to go on. This shows the systems we now are using. We both use, we also use a Michelson interferometer, which is shown here. The Michelson interferometer, what happens is you put your sample in one leg and you get illumination in both directions, and you can do a little better. But what we do now is, for example, in this interferometer, we actually have a digital phase shifter that shifts this mirror at for different phase shifts, and we can get up to 10 holograms and get very robust results. Okay, that shows you thin samples, imaging thin samples. What about three-dimensional objects? I said that one of the defects of normal microscopy is it has to be thin. What about thick samples? Well, let's look at it first of a problem, a classical problem that my good friend Robert Porter, who was my boss at Schlumberger and is here, he wrote some of the original papers on this, which is called the inverse source problem. Let's look at this. We have a source, a three-dimensional source radiating out. It's a primary source. It's not a scatterer. And we have a plane. The wave field that comes out now will be evanescent waves going up and down this plane, and homogeneous waves propagating up. Now, if I define the unit vector S, the x, y, and z components, alpha is the polar angle, and beta is the azimuthal angle around this plane here. Well, it turns out then I can do a plane wave expansion. I can write that plane wave expansion we had before. I can write it in this form, an angle form, where this contour integration here, where I integrate over all real beta, 2 pi beta. But alpha gets integrated, homogeneous wave from 0 to pi by 2. Those are the homogeneous waves that propagate out there. And then the evanescent waves come up from 0 to pi by 2 plus I infinity. We actually use a complex contour there. But this, so you've got this total field, the total radiated field consists of homogeneous waves and evanescent waves. Now it turns out that this amplitude of the plane waves, very nicely, is simply the spatial Fourier transform of this guy here, evaluated when its wave vector k is the wave number times the unit vector s. So your plane wave amplitude there, which you can determine in experiments, is directly related to the Fourier transform, spatial Fourier transform of that guy. So the inverse problem from measuring the field to estimate Q is estimate Q from specification of its Fourier transform over a sphere of radius A. Here's a picture of that. Here I just show a plane, but let's say the spatial Fourier transform of the source is this colored region here. It's distributed over the plane, of course. What I can measure is A of S, which tells me what this is over a sphere of radius K. So you have a function of 3 variables, and you know it exactly, or very well, over a sphere of radius A. K. So I remember when I first ran into this as a graduate student at the University of Rochester, and I went to my thesis advisor, Emma Wolf, at Rochester, and I said, oh, I can do this inverse problem because I can solve it exactly. I know this function over a sphere of radius K, and you can show that this is an entire analytic function of K. I says, I can analytically continue, I can do all this. He says, first of all, you can't analytically continue on a computer. Secondly, it says this is a function of 3 variables. It's specified, even though it's analytic, you have to know it over a volume in K-space rather than a surface. So it turns out this is a highly non-unique problem. It's very hard to get good images of Q from just the radiated field. In particular, it led us to study these things called non-radiating sources, which are very fascinating things in their own right. These are sources to a field that produce no radiation at all outside their volume. They absolute zero radiation, not just no evanescent, none at all, no field at all. And you can see how you get them. If I take a Fourier transform of a non-radiating source, it's equal to k squared minus little k squared times this Fourier transform of any object at all, as long as it's continuous with continuous first derivatives and compactly supported. An inverse Fourier transform gives you a non-radiating source, which is simply the Helmholtz operator operating on any function of compact support. So these non-radiating sources, there's an infinite variety of them, makes the imaging for 3-dimensional sources highly non-unique. So what you've got to do, you've got to look at what we call a pseudo-inverse solution. You choose, out of the infinite variety, you choose one reconstruction, and we usually choose the one that has minimum L2 norm. Why do we do that? Because we can compute it mathematically. And it turns out, if you expand the radiation pattern of the source, which is a directly measurable observable, into a superposition of spherical harmonics, your minimum energy source is simply given by these same expansion coefficients. You just replace the spherical harmonics by the spherical Bessel functions times YLM spherical harmonics, whose argument is now the angles of the R vector, and that gives you a solution. This was one thing that I published with my good friend Bob in Joseph many, many years ago. Now, no talk to Professor Ishimaru would be complete unless I had some sort of randomness in it. I've got to have some sort of problem that deals with random inverse problems. And this is a problem I worked on many years ago and is now actually being used. I have a friend, David Brady, at Duke, who does optics, and he's now using this stuff in some actual measurements. I mean, I did it because I thought it was an interesting problem mathematically, but it turns out it actually has some use. Here it is. I'm going to again talk about a source radiating out waves. And I'm going to go in the far field. I'm going to make my measurements far from the source. And it turns out that if I go in some direction S1 at some large distance, the field I will measure is an outgoing spherical wave with an amplitude, we'll call it A of S1. If I go in some other direction, I'll have a spherical wave A of S2. And what I'm going to do is I'm going to cross-correlate these guys. I'm going to assume that this source is random. It's a realization of a random, a 3-dimensional random process. And so I'm going to cross-correlate these guys and measure what we call the 2-point mutual coherence function, which I'll call, so this denotes an ensemble average, A star of S2, S1. And if you remember the relationship between A of S and the source transform from a previous slide, this is simply the correlation of the 4 spatial Fourier transforms, with K being the wavelength. Now, if you restrict yourself to a spatially incoherent source, what is a spatially incoherent source again? That's a source that the points radiate independently. There's no correlation at the source between the radiating points. It turns out that then this cross-correlation of Q is an intensity distribution times a delta function. And if you make use of that in here, you find out that this measured correlation is the Fourier transform of this intensity distribution, evaluated at K S2 minus S1 dot R. And this is exact. There's no approximations in this theory, as long as it's spatially incoherent source. So how can we do an incoherent source inversion? Well, here shows the coherent source that we already covered. You only know the Fourier transform of the source over that sphere. But for incoherent sources, it's a little bit different. What we've just found is we know the Fourier transform on a sphere whose center is minus K S1 and whose radius coming out is K, and then it projects out of there to KS2. So you know it of a sphere centered at minus KS1. So if I change my points as I move in my measurement plane from different S1 and S2 points, I can determine the Fourier transform throughout what we call an evolved limiting sphere, a sphere of radius 2K in Fourier space, throughout the interior, not a surface, but throughout the interior. So I can then get an estimate of the intensity distribution by just doing an inverse. I put this all information together in a clever way, and I can do this inverse Fourier transform, and I can get what we call a low-pass version of this guy here. Well, it turns out this is going from all this data to get this, to estimate this within the volumes, is not trivial. And in the 1980s, I devised a formula that I published in, I believe it was Optics Letters, to show that you could actually, there's an exact relationship between this Fourier transform on these spheres, this guy here, and its low-pass filtered version, and it's this formula here. And so this is an exact mathematical representation. And now I use the fact that our measurements, this is equal to our correlation measurements, and I get an inversion formula. And this is very, very fast, very efficient, and it's what my friend David Brady has been using in his work. Okay, another important area of research is what we call inverse scattering, or inverse potential scattering. Here I show a scatter potential V of R, and I illuminate with a plane wave propagating in the S0 direction, and I measure the scattered field in some direction S. And if I go far enough away, what I'll measure is, again, an outgoing spherical wave with an amplitude, F of S, S0, which is called the scattering amplitude of this object. Now, the total field satisfies this equation, which is the scattered field equation. V is the potential scattering potential. K is, again, the wave number. You've got this guy embedded in free space. Asymptotically, as you go far away, the field is the incident wave plus the scattered wave. So as I go far away, that's the scattered wave, and I'll always have this incident wave present. So that's my asymptotic condition. Now, one thing that we've worked with over the years are linearized approximations. The problem is scattering is a linear operation from the incident field to the scattered field. So if I look at the transform that takes the incident wave to the scattered wave, it's totally linear. The problem is the relationship between this scattering potential and the field is nonlinear. Highly nonlinear, non-local. And so an inverse problem involving this is very difficult, if not impossible. And most people, in fact, everyone I know, has given up trying to do it exactly, at least in more than one space dimension. So what we do is linearizing approximations. In the old days, what we always used, and this is still used quite a bit, is the Born approximation. And if I make the Born approximation, which is a single scattering approximation, it turns out this scattering amplitude is very easily related to V. Again, Fourier transforms. We find that this is simply the Fourier transform of this scattering potential evaluated on the sphere K S minus S naught. Now this should becoming familiar because we just saw in the inverse random source problem that the relationship between the two-point correlation function and the intensity distribution was this guy here evaluated on the spheres K S2 minus S1, and we have the same thing here, K S minus S0. By convention, we don't call what we just call the scattered direction S and the incident version S0. This is the foundation for the standard methods for doing X-ray crystallography. There one takes a scattering object and crystallizes it so that it's spread over a regular structure, crystalline structure, and then they do their scattering experiments and use the Born approximation to try to get the structure itself. The reason they crystallize it is to get the intensities, the scatter wave intensities, high enough that they can measure them with a good signal and noise. So there's our Born approximation, and we can use the handy-dandy formula I showed you before. So we know that the estimate of V is simply given by this expression, where now, in place of its transform, I use the measured data. Now this little innocent-looking thing I use to derive what is called a filtered back propagation algorithm, which has been used for many, many years in problems in diffraction tomography and inverse scattering. But it all comes about by just rewriting this in a way that is computationally efficient. And I show that on the next slide. Here's how filtered backpropagation works. You have an object that you want to construct or reconstruct. You put an incident plane wave and you measure the field over some aperture. The first step is you can show that there's a two-dimensional convolutional filter you can apply to get what we call the filtered data, filtered scattered field data. Then you backpropagate, the same backpropagation we saw at the beginning of the talk, and you generate a partial image. It's the image from that direction. Then you change the direction of illumination. You do the same thing, and you add up all of those partial images, and you end up with a reconstruction. And that's nothing but this rewritten in a little better form. Now, do we do optical experiment? How do we do thick samples in optics in my lab? Well, now all we do is we put our sample on a gimbaled mount, and we make many, many measurements by rotating it about and doing the inversions. I haven't, because of time, I'm not going to show you any examples on this, but I will show you examples of this type of thing on a study we've been doing for the Department of Energy. This shows an artist's conception of a pit that the Department of Energy has used to throw nuclear waste for years and years and years. And what they do is they just tumble these canisters that contain low-level nuclear waste into a pit and then cover it with dirt and pack it down and say, okay, the problem's gone away. And of course, the problem hasn't gone away, and we are now left with horrendous cleanup efforts. So we just finished a project for DOE looking at this issue in what is called Pit 9, which is one of the pits that they have all this into. And what we've done, or what they've done, is they've drilled boreholes in throughout this thing, and we've put sources and receivers and done diffraction tomographic imaging of this Pit 9. So here's shows a hole. It's about 20 feet long, and we have an array of microphones, acoustic microphones, up to, I think we used 32 in this study. And on the surface, we have a little metal plate that we bang, sends a sound wave down, reflects off that, scatters field, we measure it here, and we use these filtered backpropagation. And we do this for a whole bunch of holes. This just shows, 4 holes. And we put all this data together to generate a reconstruction. So the idea, we use acoustic diffraction tomography, sources, produce waves that scatter, and are measured down in a borehole with an acoustic receivers. Now, people say I don't do experiments. I just show this slide to prove otherwise. This is our favorite geophysicist, Heidi. This is me in a hard hat. This was taken about 5 years ago. This was one of the graduate students from University of Oklahoma, and this is one of the students from Northeastern. This was a joint Oklahoma-Northeastern study. This is not a very flattering picture of one of the graduate students hitting the metal hammer, hitting the plate. This is Greg. And what he's doing, he's hitting a metal plate that puts the sound waves down into the earth, and you see the borehole there, and those waves will propagate, scatter, and it will be picked up by the microphones in the array. Now you'd say, how can such a rudimentary system ever work? Well, we thought that too at the beginning, and we got surprising results. This just shows all the boreholes. These are, for example, here's a borehole. Then we have to put a whole line of these are different positions of the plate that we hit. So it takes a long time to do these experiments. This is just a typical image we get, an anomaly image. This shows a three-dimensional image, and what we're looking at, these are groups of barrels, and what we're really looking for is leaching from those barrels. And I could show you hundreds and hundreds of images of this sort. The analysis of those images is very difficult and is not completed. During the study, of course, the Department of Energy came and said, well, how do we know these images you're generating have any validity? You can just show us blobs. We don't know what's down there. So we said, well, we thought about it, and my good friend, who's actually just passed away the year before last with a heart attack, Alan Whitten, who's my colleague on this project, he came up with a brilliant idea. He says, let's threshold everything and image the boreholes. Everybody knows those boreholes are down there, and they won't argue. And there is an image we got of the 4 ball holes. This one's distorted because we didn't have lines, receiver lines, enough receiver lines. But when we showed them this, they continued the project for 3 years. So they were happy. Okay, the last thing I'm going to talk about is inverse surface scattering. This is an interesting topic that I've gotten into recently with a colleague of mine, Russell Luke, in the Department of Mathematics at the University of Delaware. We've been looking at this problem and have gotten some interesting results. And I want to show you how it was done, how it's been done, different approaches to it, again, because it's Fourier. Here shows a scattering circuit. Now this is we have 2 types of scattering we can have. We can have scattering where the field actually penetrates into the scatter, and that's the potential scattering I showed earlier. But you can also have structures where, for example, a conductor, the field can't penetrate in, and we call those surface scatters. A Dirichlet scatter is just a mathematician's term for a conducting surface in electromagnetics, for example. It's one where the total field must vanish over the surface. So we put a plane wave in, it scatters just like before, and we're going to have a scattering amplitude. That's the scattered field that was the result. The difference is the relationship between the scattering amplitude, which we can measure, for example, different S0 in different scattering directions, and the scatterer is this expression here. It's an integral over the surface. There's no 3-dimensional integral here, and it involves the normal derivative of the field on the boundary of the surface. And this is the same friend, the Fourier kernel, e minus I k s dot r. Now the inverse problem. Estimate the surface. I want you to tell me what the surface is from knowing this. Well, the big problem you see is you don't know the normal derivative of the field over this boundary. You know the total field must vanish, but you don't know what the field is. What can you do? Well, you can use an approximation, or you can be clever. And both have been used. Let me first of all talk about using an approximation. The standard approximation that has been used is called the physical optics approximation, which actually works extremely well. Here I show a plane wave coming into an object, and I made this object a very simple object. I'm going to restrict our attention to convex surfaces. Convex surfaces are such that you can attach a plane at every point on the surface, and the plane only has one point of tangency. So it's a nice smooth surface. It doesn't have any holes in it. It doesn't have any little jumps. So here's the incident plane wave comes in. Now what's going to happen is, to a good first approximation, that plane wave will light up part of the surface and the other surface will be in shadow. So you'll get bright here and you'll get no wave, a very small field here. That's the physical optics approximation. You assume that you're going to have the total field is simply going to be such that you're going to get a lit region and an unlit region, and you're going to assume that the wavelength is sufficiently small that the total field on here, the normal derivative of the total field, is twice the normal derivative of the incident field. So if you do that, you end up with what we call the physical optics approximation to this guy here. And it turns out to be this very simple integral here. And now you've gotten rid of this because you've made the physical optics approximation. By the way, K0 here is now my new wave number. Some of these are older slides. In some slides I use K, some K0. I apologize for that. Now, there was a fellow many years ago named Bojaski. Now, Bojaski had one thing that he did that is really very clever. He did a number of things clever. One was what is called a Bojaski transformation. What he did was he showed that if you take and construct the object G of S0, well, first of all, what he wants to do is only look in the backscatter direction. So let's say I illuminate from here, and I don't measure at all angles S. I only measure back at the backscatter direction. We call that the backscattering amplitude. So I measure incident back. Now let me also make one other experiment. Let me illuminate from here and measure that. So that would be F of S0 minus S0. It turns out if you do those two measurements and you define a structure G of S0, that you can show that from this expression, that object G of S naught is equal to the Fourier transform, is proportional to the Fourier transform of what we call the characteristic function of the object. The characteristic function of the object is 1 if you're in the object, 0 outside. So by making the Bojarsky transformation, you're able to relate this measured quantity to the Fourier transform. And now again, we're back to measuring the Fourier transform on a sphere, and it turns out you can now fill in all the data and you can get inversions. But in this formulation, you have to use not many different angles, you're using many different wavelengths. You have to let K naught vary, but it actually works quite well. What about beyond physical optics? What do we do if we go beyond physical optics? Well, now we're in a situation where we've got to do a more careful formulation of this. Here I show, now we go back to our plane wave expansion. They all go back to Fourier, they all go back to plane wave expansion. Remember I said if you have a wave field that is in free space, and I limit some region of free space, I can express it in a superposition of plane waves, all of them homogeneous. And that's an exact result. So if I have an incident wave, an arbitrary, not a plane wave, an arbitrary incident wave coming into a structure, I can express it as a superposition of plane waves, and they're all homogeneous. So this is over 4 pi to the radius. That incident wave will come in, scatter, and produce a scattered wave, and it turns out that that, of course, can be represented in plane wave expansion of a different type. There I have to include homogeneous waves and evanescent waves as evidenced by this complex contour. If you go far into the distance, far away from the object, this plane wave expansion, as we've seen, reduces to what we call the scattering amplitude times e to the I k naught r over r. Now, why do I do this? Because we're going to be using this to get a exact formulation of the inverse problem that actually works quite well in practice. The key to that is that these are not independent. If I know the plane wave amplitude of the incident wave, I can get the plane wave amplitude of the scattered wave through this very simple equation. So it says the plane wave amplitude of the scattered wave is equal to the plane wave amplitude of the incident wave convolved with the scattering amplitude of the object. This is integrated over 4 pi to the radius. So I can express the scattered wave exactly in that way. Now we're going to come back to this in a moment to solve the problem. So let's go and look at this formulation, the exact formulation of inverse scattering from a surface. We have an incident wave, surface, wave comes out, and we want to determine this surface. And we're going to assume a Dirichlet object. A Dirichlet object, again, is a conductor, say, where the total field must vanish over the surface. Now, how can I solve this problem and not use the physical optics approximation? Well, one way of doing that, an inversion algorithm, is let me compute the incident and scattered waves exactly outside the object and use this expression. Now, I can actually do that. If I know the incident wave, I know this incident plane wave amplitude. If I know the scat, I can back propagate the scattered wave in principle and get the scattered wave everywhere outside this object, including right on the boundary. The incident wave, again, I assume I know it, so I just apply this algorithm, and wherever this sum is 0, that tells me that's the object. So you compute the incident scattered waves and use it. Now, the problem is, now this has been tried. The first trial of this was a very famous paper by Raj Mitra and Imbrial many, many years ago, published in the IEEE, and it actually worked quite well. Bob Porter actually published a paper with Weng Chu a number of years ago on a different variety or a different method of doing this. But both of them were approximating. The reason is, and they only have limited success, because you cannot compute the evanescent component of the scattered field. Remember, if you back propagate, as we talked earlier, you can't get the evanescent wave. So the wave field that you end up back propagating has limited angular resolution, and you wouldn't be able to see the fine detail in the object, the scattered surface. So that's a problem. So what are the solutions? Well, ad hoc approximations, and my good friend David Colton at Delaware has been developing what is called the linear sampling theory method, which actually does work quite well and is actually a competitor of what we've been selling. Our new approach is we select the incident field so the scattered field is approximately 0. And I'll explain more about how we can do this. By doing this, you go to this expression, you don't need the scattered field. You don't have to back propagate it. You just take that incident wave that you've computed and you set it wherever it's 0, that's the surface of the scatter. And that leads to this idea of waves. I can actually design waves that don't scatter off objects. I can design incident waves that have the property that they basically don't scatter. So let's look at how this is done. Here's an expression for the scattered wave. It involves this integration over the real evanescent and homogeneous waves asymptotically. It's an alcoholic spherical wave. And now here's my object, and this is the wave coming out. I get evanescent waves going up and down, and homogeneous waves, and the evanescent waves decay exponentially as I get far away. What we're going to do is the singular value decomposition of the scattering amplitude. Now remember, I showed this expression earlier, that I showed the expression that the amplitude of the scattered waves are related to the amplitude of the incident wave through this mapping. Turns out this is a compact operator, a compact mapping, and we can do an SVD of it. So we actually do an SVD, we calculate the what we call the singular vectors of the incident wave and the singular vectors of the scattered wave. These are orthonormal sets that are orthonormal. They're orthonormal on the unit sphere. Orthonormal on the unit sphere. And I can expand the incident plane wave amplitude in that set, V sub p. I can expand the scattered wave amplitude in that set, U sub p. And because of this relationship, I find that if I expand the incident wave in those V sub p's, the scattered wave has this expansion, the same amplitudes here, A sub p, multiplied by sigma sub p. Now the key is, we've been able to show that for convex objects, shapes that are convex, compactly supported, these sigma sub p's have a point. There is a p, the index p, where they drop off exponentially fast. So if I design my incident plane wave amplitude so it's 0, where the sigma sub p's are big, in other words over that region, the scattered wave will be approximately 0 because it's multiplied. These are exponentially fast decaying, and I can get my scattered wave to be approximately 0. So this shows this in terms of waves. There's the incident wave, scattered wave, and these are multiplied by these sigma sub p's, which cause it to go to 0. So we call these non-scattering incident waves, incident fields. We just published a paper in SciAm, Journal of Applied Mathematics, Russell Luke and myself on this, and we now have another paper going into the IEEE, and it's really quite fascinating stuff. Here I have an example, and I'll end with this example. Well, let me give you the summary of the procedure. The first step in the procedure is you measure the scattering amplitude for different scattering incident plane waves. So you know this. You do an SVD. Get these, and these. You now compute the non-scattering incident field, where I sum over arbitrary coefficients as long as sigma sub p is smaller than some number, and I apply the boundary conditions, psi sub I equal to 0, and you'll get the surface of the thing. Here's a toy example that I'll end with. Here's a cylinder of some radius A, and it turns out you can easily get the expression for the scattering amplitude. You can compute the singular vectors. You can do everything, and here shows the singular values. And I've taken cylinders of different radii. And you see each of them have a breakpoint. This is a log here, where the singular values start decaying. Here shows just a plot of an incident plane wave. This is the intensity distribution. This is the real part of an incident plane wave over some region. This shows the real part of the scattered wave from a cylinder. And you see the scattered wave comes out. You get the forward scattering coming out here and the back scattering coming up here. This shows the real part of, now I break the incident wave into maximally and minimally scattering parts. This shows the real part of the maximally scattering component, and this is the real part of the minimally scattering component. And if you look here, you can easily get, or at least I can see that you can get, if you look at the real part of the minimally scattering part of the incident wave, there's the region. You can pick it out quite accurately, and it does work. So this is what we've been doing, and let me just mention one more thing before I end. How do you go beyond Fourier? How can we do better? Well, one of the things that we've been doing over the last 5 or 6 years is looking at all of these problems when you have a background medium, not free space. For example, you might have a source embedded in some medium here that varies spatially. It has a different index of refraction as a function of position. And what we do is we want to now reformulate, for example, the source problem. So now our source, it's not a constant k, but it can vary due to a background. You can then write all the expressions in terms of a Green's function, but now this is what we call a background Green's function. It's not the Green's function for free space. And what replaces the plane waves then? Well, the thing that replaces the plane waves is you take this region and you put an incident wave in and you look at the scattered wave that results. Those guys there, these scattered waves that result, are the scattering wave states of the background, we call them, and they replace the plane waves. Now you see, if the background was 0, this quantity vanishes and you just get a plane wave. When the background is there, these things now have structure, and everything gets replaced by these. Fourier analysis goes over to the singular value decomposition. Everything becomes the SVD, but it all goes through. It's just a little more complicated. Well, I want to end now, and again I want to thank the organizers for inviting me. It's a great, great honor, my honor, to be here for such a great, great person. Thank you.
Questions?
Yes?
When you arrange to have the scattered field be 0, the non-radiating, I'm wondering, is the condition where the incident field 0, is that unique?
It turns out, you mean is there only one incident field? No, the incident field is totally arbitrary. What has to happen is all you require is that its components, let's see, here's the expression. Its components over the, here's the incident wave. All I require is that it includes singular functions such that their singular value is smaller than some epsilon. But I can choose it totally arbitrary. But basically you're saying, I don't want that incident wave to have any components that will scatter off the object. Okay, and it's quite remarkable, but this works quite accurately. We've looked, by the way, at this formulation in looking at cloaking of objects. Cloaked, you're probably reading all the stuff on metamaterial. A cloaked object is an object that an incident wave comes in and it's totally transparent. The incident wave just goes through on no effect at all. Now we've looked at this formulation within cloaking also. But it's as long as you give me this guy here, I can compute this SVD, and there's always some breakpoint where these singular values go to 0 exponentially fast. Yes?
So to do this one here, you are going to go through the integral equation to get the singular value?
Yeah, what we do, yes, we measure, again, Professor Kuga earlier said to me in his office, he said, well, you have to measure the scattering amplitude at all angles of incident, all scattering directions. And looked at me kind of skeptical. And I said, yes, but this is mathematics. So, you know, you're going to say, well, can I actually use this in practice? First of all, probably not. But it opens inroads to other things. For example, cloaking of objects and so on. This is just one application. But the answer is yes. We assume we know this. And then what we do is we actually, of course, we discretize this. And, or in some cases, you can represent this in a modal expansion if you have a separable, for example, separable surface. We can do it in a way. We actually do the decomposition. And of course, a friend of mine, Vladimir Rocklin at Yale, has a very, very fast very fast method for doing the singularity decomposition now. That is order of n log n as opposed to n4. So we've been using his routine, and we do the SPD very quickly, and then we just throw away all the components which are strongly scattered. It's kind of interesting. It says to solve an inverse scattering problem, you use the part of the field that doesn't scatter. But it actually is interesting.
I think we need to vacate this room soon, so yes. Thank you very much.
You see Paul Carlson now?